In this video, I'm going to elaborate a little bit on the physical meaning and interpretation of operators in quantum mechanics, and in particular we're going to discuss a very important class of problems that appear throughout quantum mechanics, that is so-called eigenvalue problems. To see how what they are and how they arise, let me first write down the time-dependent Schrödinger equation, the canonical time-dependent Schrödinger equation, but specifically with the time-independent Hamiltonian. So physically this means that the potential in which our quantum particle is moving is not time-dependent, and actually most problems we're going to see fall into this category. So it's a very reasonable assumption, so that neither the mass nor the potential are time-dependent. So in this case, it turns out there is absolutely no need to deal with this complicated differential equation, partial differential equation that involves the time derivative. So the time dependence can be sort of factored out of the equation in a very straightforward way, and this is accomplished by performing separation of variables. So basically what we can say is, let's look for our solution in the following form. So the full wave function is going to be a product of some time-independent piece, psi of r, and this exponential, which is sort of left over from the plane wave. So this psi of r does not have to be a plane wave if the potential exists, but it is not a plane wave if there is a potential, but the time dependence sort of remains the same. And so if we plug in this ansatz into the Schrödinger equation, so we're going to have in the left-hand side the derivative with respect to time, psi of r, e to the power minus I energy t over h bar. So I should mention that E, of course, corresponds to the energy. And so since this lowercase psi of r does not depend on time, we don't have to differentiate this part. We're going to differentiate just the exponential, and just essentially by construction we're going to get in the left-hand side E psi of r and this exponential. On the other hand, the right-hand side, since there is nothing time dependent there, simply reads the Hamiltonian acting on the position dependent part. And the exponential is also here, but it's sort of irrelevant in the sense that the Hamiltonian doesn't see it. So the Hamiltonian only involves either derivative with respect to spatial coordinates or the potential, which is just multiplication operator. So we see that both sides of this equation contain this exponential, and so we can just cancel this exponential, and we're left with, let me just switch the order in which these guys appear. So we're left with the following equation: h acting on psi of r is equal to E times psi of r. And this is what is known as time-independent Schrödinger equation, or stationary Schrödinger equation. So this category of problems where an operator acting on a vector in some space reproduces the same vector multiplied by some number. So this category of problems in math are called eigenvalue problems. And in the context of this mathematical theory, psi here represents what's known as eigenvector. Let me write it. And E is an eigenvalue of the corresponding operator. In this case, this operator is Hamiltonian. Now, let me tell you from the outset, we shall discuss it in more details later, that the physical significance of these eigenvalues is in that they determine the possible outcomes of experiment that actually measure, in this case, energy. So we know that, for instance, in classical physics, if I were to have some potential well, so let's say this is my v of x, and there's some potential well, just one example of problems that we're actually going to study. So if I had a classical particle, I would be able to put a classical particle with any energy in this well. It would just oscillate between the two turning points if there is no friction, and I can do so for any value of energy. It turns out that in quantum mechanics it's not necessarily so. Well, it's not so, and the range of available energy is limited in this case. So what I would have is a discrete, so-called discrete spectrum, by which I mean possible solutions to this equation. So these levels, so let's say E1 or E2, are going to come out of this eigenvalue problem naturally. So we see that an eigenvalue problem for the Hamiltonian arises naturally from the original Schrödinger equation. And as such, it becomes a very important independent, in some sense, equation of quantum theory. And actually, oftentimes when we say Schrödinger equation, we actually refer to this h psi equals e psi, not to the original one with the time derivative. And furthermore, so eigenvalue problems also appear for other operators in quantum theory. So it's very important, and we should know at least a few basic things, basic properties of such eigenvalue problems and the operators involved in these eigenvalue problems. So we don't have time now to go into comprehensive theory of this, mathematical theory, which could be in principle a subject of a year-long course. So therefore I will just emphasize a few things that are really crucial for the future, and also introduce some notations and terms that are important. So one such important thing is the notion of a Hermitian operator that is defined by the following relation. So let's imagine we have an operator A acting in a space of functions psi of r. So I'm not going to define precisely mathematically what this space is, but we should just think about wave functions that describe the properties of our quantum particles. So one can define a Hermitian adjoint operator A dagger to the operator A by the following relation. So the left-hand side of this equation is essentially identical to what we saw in the previous video when we defined an average or an expectation value of an operator A. It's an integral over the entire space of psi star, let's say our wave function, times the action of our operator A on psi. And the operator A dagger sort of moves from the right to the left and now acts on the function which is complex conjugate. And so if the two expressions are equal for any psi of r, then we have found the Hermitian adjoint operator. And an important class of operators that appear in quantum mechanics are called Hermitian operators, and they're characterized by the fact that their Hermitian adjoint is equal to the operator itself. So they are called Hermitian. The importance of the Hermitian operators manifests itself if we look at their properties, the properties of their eigenvalue problem. So in general, if we have an eigenvalue problem for an arbitrary operator, there is no guarantee that its eigenvalues are going to be real. So in the context of quantum physics, this would lead to a bit of a problem because, well, let's say if we have a wave function which is described by, let's say, psi sub a, and we want to measure the expectation value of the quantity corresponding to this operator a. So we will calculate this average value, and we're going to get, if a is complex, we're going to get an expectation value which is complex. And it sort of, in most cases, doesn't make sense. So, for example, if we measure energy of a particle, we certainly don't want to get I, the measuring constant I. We want to get a reasonable number that has sort of its counterpart in classical physics, which does not know about complex numbers. So what I'm saying here is that if we want to describe physically reasonable quantities, so we want these operators to give rise to real eigenvalues. So this would make sense. And the Hermitian operators have this property, exactly this property. So the eigenvalues of Hermitian operators are all real. So another crucially important property of the eigenvalue problem for a Hermitian operator is that its eigenvectors, these solutions psi sub a of r to this equation, form a basis in an appropriate space. So that is a space where our functions live. So for instance, in the context of quantum physics, these are going to be wave functions. And of course, I should mention that the statements I'm making are not mathematically rigorous statements. So if you want to see a precise definition or a theorem, so there is, of course, very rich mathematical literature on the subject, and I would encourage you to look into this. But at this stage, I just want to give you an idea about the properties. And so the property that I'm presenting here is that essentially if you have any relevant function psi of r, which has something to do with our problem, and this function sort of lives in the space where our operator acts, so then a set of all eigenvectors of this operator, which in principle can be either discrete or continuous, in which case I would have written an integral, even both. So, but in any case, any such wave function can be represented as a linear combination of the eigenfunctions of the operator E. And this has very important consequences, as I said, in quantum physics. Now, going closer to quantum physics and further away from sort of mathematical statements, let me just summarize things that really are important in the context of quantum mechanics. So the first statement here is that physical observables, essentially things that we want to measure in quantum mechanics, are described by Hermitian operators, sometimes also called self-adjoint operators. So I should mention that there exists a subtle difference, actually mathematically, between the Hermitian and self-adjoint operators, but it involves rather complicated math, and in the framework of this course we can just consider Hermitian and self-adjoint to be the same thing. But if among you there are some math aficionados who want to know the difference, ask this question in the discussion forum, and I would be happy to elaborate on this. But anyway, so if we have identified a quantity of interest, our observable A, and identified an operator associated with this observable, so then we need to solve the eigenvalue problem for this operator. And the available eigenvalues, they determine possible values that actually can be measured in experiment. So also let me reiterate a very important fact we just discussed in the previous slide, and we're going to talk a little bit about this in the next video, namely that the solutions to this eigenvalue problem, these functions psi sub A of R, form a basis in the space where our wave functions live. Which implies that any wave function describing a physical state of a system can be expanded as a linear combination of these eigenvectors. So the last comment, but not the least important, that I'm going to make relates to the interpretation of these coefficients C sub A, the complex numbers that appear in this expansion. As a matter of fact, actually, this is probably the most important take-home message that I would like you to take out of this slide. So imagine that we have an ensemble of identical quantum systems, which exist in exactly the same quantum state described by some wave function psi that we expanded in our basis of these eigenstates. And let's imagine that we're going to perform, let's say, 3 identical measurements of the identical quantity A. So we want to measure A in exactly the same way with exactly the same kinds of systems. So the weird thing about quantum mechanics is that even though everything is the same about these systems, we're actually going to get, strictly speaking, generally 3 different results. So there is a chance some of them will be the same, but there's no guarantee at all. And the probability of finding a system in a certain state, which sometimes is referred to as a collapse of a wave function into a certain eigenstate. So this probability, let me call it W sub A, is equal to the absolute value squared of the coefficients in this expansion. So this is the probability. So in this example, again, so what we can say for sure, the only thing we can say for sure is that all these measurements are going to result in a value of A that belongs to the spectrum, that is, to the set of available eigenvalues of the operator E. But which particular value is going to be measured, we don't know. We only can say which is more likely, and we can quantify this uncertainty, but this is maximum we can do. And so this principle is actually very important in quantum mechanics, and we're going to use it later in the course very often.